Learning objectives. In this chapter, the user would learn the following aspects of groups and subgroups: group axioms, permutation groups, subgroups, cosets, normal subgroups, semigroups, free semigroups, monoids, sequential machines, error correcting codes, modular arithmetic grammars. Groups. Abstract algebra is the study of algebraic structures. Such a structure consists of a set together with one or more binary operations which are required to satisfy certain axioms. Groups. A group is a set with an associated binary operation satisfying certain mathematical properties. This simple algebraic structure has very rich applications because the elements of the set need not be just numbers. They can be matrices, planes, translations, rotations, reflections, in fact functions or operations of any kind. Groups. Group theory has been applied in fields as diverse as crystallography and game theory. In crystallography and in quantum mechanics, groups serve as the natural language to describe the arrangement of molecules and the behavior of particles. A striking example is the discovery of the Ohm baryon, an elementary particle belonging to a family of 10 particles. It was the last member to be discovered. After the first 9 members were discovered and their behavior was modeled using group theory, it was thought there should be another particle in the family. This in turn led to a search, and the Ohm baryon was discovered in 1964. It was like someone telling you there is a gold coin in your pocket. You are unaware of its existence, but when you put your hand in the pocket, you find it there, as if by magic. Groups. A group G is a finite or infinite set together with a binary operation or composition that satisfies the 4 fundamental properties of closure, associativity, the identity property, and the inverse property. Basics of counting. The operation with respect to which a group is defined is often called the group operation, and a set is said to be a group under this operation if the following 4 properties are satisfied. Number 1. Closure. If A and B are 2 elements in G, then the product A cross B is also in G. Number 2. Associativity. The defined operation is associative for all A, B, C in G, then A cross B cross C equal to A cross B cross C. Number 3. Existence of identity. There is an identity element, often denoted by E, such that E cross A equal to A cross E equal to A for all A belonging to G. Number 4. Existence of inverse. Each element must have an inverse, that is, for each element A in G, there must exist an element B in G such that A cross B equal to B. The number of elements in the set is called the order of the group. If the set is infinite, the group is called an infinite group. Chord shuffling. A perfect shuffle is one in which the deck is cut precisely in 2 equal parts and the chords are interleaved. Example: if these cards are 1, 2, etc. 52, then 2 halves are 1, 2, etc. 26 and 27, 28, etc. 52. After a perfect shuffle, the order of the chords is either 1, 27, 2, 28, 26, 52 or 27, 1, 28, 2, etc. 52, 26 going on. 8 perfect shuffles restore a deck of 52 chords to the original order. Groups. Group theorists have studied generalization of shuffles on decks of arbitrary number of chords in detail. Magic tricks, chord shuffling, and computer memories by S. Brent Morris. In addition to their use in designing many card tricks, the group theoretic results from studying shuffles have been used to designing dynamic RAM and also in algorithms for shuffling tasks in parallel computers with multiple processors. Groups. In the Rubik's cube, the cube is formed of 27 small cubes. Each face consists of 9 small squares, which we may call facets. Since a cube has 6 faces, we have 54 facets in all. Each facet is colored with one of 6 different colors. There being exactly 9 facets of each color, the facets can be moved into different positions by various rotations. The problem consists of applying suitable rotations so that each of the 6 faces has all the 9 facets of one color. Groups. If it possible to solve the Rubik cube without knowledge of groups, but the fast algorithm which solve a cube from any initial position in 20 moves or less use group theory. A well-known book on solving the Rubik cube is a Rubik cube compendium by Erno Rubik, Thomas Verga, Gerson Kerry, Georgi Marx, and Thomas Becker D. And another one is Notes on Rubik's Magic Cube by David Singmaster. The more recent adventures in group theory, Rubik's Cube, Merlin Machine, and another mathematical toys by David Joyner, as a description of many puzzles, their solving strategies, and the underlying group theoretic framework. Groups. Groups are particularly simple algebraic structure having only one operation and 3 axioms. Most algebraic structures have more than one operation and are required to satisfy a long list of axioms. Groups. Field is an algebraic structure with addition and multiplication which obey all of the usual rules of elementary algebra. Examples of fields include the rational numbers q, p, the real numbers r, and the complex number c. A ring is a more general algebraic structure with addition and multiplication. A good example of a ring is the set of all n cross n matrices under the operations of matrix addition and matrix multiplication. A vector space is an algebraic structure with operations of addition and multiplication by scalars. The scalars are required to be elements of a field such as the real numbers r. The basic example of a vector space is the set Rn of all vectors with n entries. A module is similar to a vector space except that the scalars are only required to be elements of a ring. For example, the set Zn of n-dimensional vectors with integer entries forms a module where scalar multiplication refers to multiplication by integer scalars. Groups. Properties of groups. Uniqueness of identity element. The identity element of a group is unique. For suppose that there are 2 identity elements, say E1 and E2. This means that G composite to E1 equal to E1 composite to G equal to G for all G, and also G composite to E2 equal to E2 composite to G equal to G for all G. Then E1 equal to E1 composite to E2 equal to E2. Groups. Uniqueness of inverse. The inverse of a group element G is unique. For suppose that H and K are both additive inverses of G. This means that G composite to H equal to H composite to G equal to E, and G composite to K equal to K composite to G equal to E. We know now that there is a unique identity element E. Then H equal to H composite to E equal to H composite to G composite K equal to H composite to G composite to K equal to E composite to K equal to K, where we use the associative law. In the third step, we denote the inverse of G by G power minus 1. Groups composing more than 2 elements. As long as the associative law holds, the result of composing any number of elements is independent of the way that the product is bracketed. For example, A composite to B composite to C composite to D equal to A composite to B composite C composite to D. Since associative law holds in a group, we have proposition, let G1, G2, etc. Gn be elements of a group G, then the composition G1 composite, G2 composite, etc. composite Gn is well defined independent of the way it is bracketed. Groups, cancellation laws. Proposition in a group G, if A composite to G equal to B composite to G, then A equal to B. Similarly, if G composite to A equal to G composite to B, then A equal to B. Proof. Suppose that A composite to G equal to B composite to G and let H equal to G minus 1, then A equal to A composite to E equal to A composite to G composite to H equal to A composite to G composite H, B composite to G composite H, B composite G composite H equal to B composite E equal to B. The other law is proved similarly. Groups. Proposition. The inverse of G composite to H is H inverse composite to G inverse. Proof. G composite to H composite, H inverse composite G inverse equal to G composite H composite H inverse composite G inverse equal to G composite E composite G inverse equal to G composite G inverse equal to E. Using the associative law and similarity, H inverse composite G inverse composite G composite H equal to E. Order. The order of an element G in a group is defined as follows. If G power n equal to 1 for some positive integer n, then the smallest such n is called the order of G. If no such n exists, we say that G has infinite order. Group's order. The implies G equal to G inverse by the cancellation law. Consider the additive group of the ring Z. The element 1 has infinite order since there is no positive integer n such that n into 1 equal to 0. Identity element always has order 1. If an element G has order 2, then it is equal to its inverse for G square equal to 1 equal to G into G minus 1. Groups. Assume that the equation xyz equal to 1 holds in a group G. Does it follow that yzx equal to 1? That yxz equal to 1? Justify your answer. Solution. xyz equal to 1 implies that x of yz equal to 1. Let yz equal to a. Then we have x a equal to 1 and so ax equal to 1. Since a is invertible and a inverse equal to x, it follows that yz of x equal to 1, hence yzx equal to 1. On the other hand, if xyz equal to 1, it is not always true that yxz equal to 1. To see this, let G be the group of 2 cross 2 real matrices and let x equal to 1, 2, 0, 2. Y equal to 0, 1, 2, 1. Z equal to minus 1 by 2, 3 by 4, 1, minus 1. Then xyz equal to 1, 0, 0, 1. But yxz equal to 2, minus 2, 5, minus 9 by 2 not equal to 1. Groups. Let G be a non-empty set closed under an associative product which in addition satisfies A. There exists an E belongs to G such that AE equal to E for all A belongs to G. B. Given A belongs to G, there exists an element Y of A belongs to G such that AY of A equal to E. Prove that G must be a group under this product. Solution. Given A belongs to G, since right inverse exists, there exists y of a belongs to G such that a into y of a equal to E, then y of a equal to y of a into E equal to y of a into y of a equal to y of a into a, y of a. Also, there exists T belongs to G such that y of a into T equal to T. This implies that y of a into y of a into T equal to E, then y of a into E equal to E, hence y of a into a equal to E. So every right inverse is also a left inverse. Now for any a belongs to G, we have EA equal to a into y of a into a into y of a into a equal to AE equal to a. As E is a right identity, hence E is a left identity. Groups. If G is a group of even order, prove that it is an element A not equal to E satisfying A square equal to E. Solution. Define a relation on G by G follows H if and only if G equal to H or G equal to H inverse for all G comma H belongs to G. It is easy to see that this is an equivalence relation. The equivalence class containing G is G inverse and contains exactly two elements if and only if G square not equal to E. Let C1, C2, etc. Ck be the equivalence classes of G with respect to follows. Then modulus of G equal to modulus of C1 plus modulus of C2 plus etc. plus modulus of Ck. Since each modulus of Ci belongs to 1, 2 and the modulus of G is even, the number of equivalence classes Ci with modulus of Ci equal to 1 is even. Since the equivalence class containing E has just one element, there must exist another equivalence class with exactly one element, say A. Then E not equal to A and A inverse equal to A, that is A square equal to E. Groups. Prove that in any group the orders of AB and of BA are equal. Solution. Let AB whole power k equal to 1, then AB etc. AB equal to 1. This implies A, BA etc. BA, B equal to 1. We have A, BA whole power k minus 1, B equal to 1 implies BA whole power k minus 1 equal to A power minus 1 into B power minus 1 equal to BA whole power minus 1. We obtain BA whole power k minus 1 into BA equal to 1, which implies BA whole power k equal to 1. Similarly, if BA whole power 1 equal to 1, then AB whole power 1 equal to 1. Hence, orders of AB and BA are the same. Groups. Compute A inverse BA where A equal to 135, 12, where B equal to 1579. Solution. A inverse equal to 12531. A inverse BA equal to 12531, 1579, 135, 12 equal to 3795. Subgroups. From the table, it follows that S is closed under multiplication. Associativity holds in S since it is true for G. Identity element is 1, inverse of 1, minus 1 or respectively 1, minus 1. Thus S is a group of G. Note, if S equal to 1, I, then S is not a subgroup of G, for it is not closed under multiplication. Therefore, I equal to minus 1 not belongs to S. R comma plus is a subgroup of C comma plus. Q comma plus is a subgroup of R comma plus. R power plus comma X is a subgroup of R comma X. The set E of even integers is a subgroup of the additive group of integers. Subgroups. Example 2. Normalizer of an element. If A belongs to G, define n of A equal to x belongs to G such that Ax equal to xa. Show that n of A is a subgroup of G. Solution. N of A consists of those elements in G which commutative with A. Let x comma y belongs to n of a, then ax equal to xa and ay equal to ya. Therefore, xy of a equal to x of ya equal to x of ay equal to xa of y equal to ax of y equal to a of xy. Hence, xy belongs to n of a. From ax equal to xa, we get x inverse ax, x inverse equal to x inverse xa, x inverse implies x inverse a, x inverse equal to x inverse x, ax inverse. X inverse a equal to ax inverse, so that x inverse belongs to n of a. Cosets ah such that h belongs to h is called a left coset of h in G. Any set of the type HA equal to HA such that h belongs to h is called a right. If h is a subgroup of G, then h itself is a left coset as well as a right coset. For h equal to EH, h belongs to h equal to h such that h belongs to h equal to h, and HE equal to HE such that h equal to h such that h belongs to h equal to h. Since h is a subgroup of G, the identity element E belongs to h. Therefore, for A belongs to G, AE belongs to AH, and EA belongs to HA implies A belongs to HA. Thus, every left-right coset of H is non-empty. If G is abelian, then AH equal to HA for every H belongs to H. Therefore, AH equal to H such that H belongs to H equal to HA. But in general, AH not equal to HA. Example, let G equal to -1, -1, minus I. H equal to -1, 1. Then HI equal to -I. H cross 1 equal to -1, 1. H cross -1 equal to 1, 1. And H cross -I equal to I minus I. Thus, there are only two right cosets H and HI of H in G. High H equal to -I, 1 cross H equal to -1, 1, -1 cross H equal to 1 minus 1, and -IH equal to I minus I. There are only two left cosets H and IH of H in G. Cosets. The cosets, we have introduced the product, sum and the subtraction rules for counting. You may wonder whether there is also a cosets for counting. In fact, there is such a rule which can be useful when solving certain types of enumeration problems. The cosets, there are n by d ways to do a task if it can be done using procedure that can be carried out in n ways, and for every way w, exactly d of the n ways correspond to way w. Conclusion. In this chapter, the user have covered the following aspects of groups and subgroups: group axioms, permutation groups, subgroups, cosets, normal subgroups, semigroups, free semigroups, monoids, sequential machines, error correcting codes, modular arithmetic grammars,